And in the second video of today, I'll cover two topics: general eccentric loading and stress concentration briefly. Yeah, because I don't think it's conceptually very new, so I'll just to make a simple discussion about it, and yeah, you'll be able to figure it out by yourself. And regarding stress concentration, it's the same. Yeah, I'm gonna just tell you the geometry, and from the geometry and this table you can figure out the stress intensification factor K from this table. But yeah, anyway, let me give you some explanation. So until now, yeah, we consider it's like a eccentric loading when P is located like a in like a y-axis, right? Instead of locating like a P in y-axis, you can think about having P in any kind of point in YZ plane. Okay, suppose that you have P acting on like a distance B from the centroid in y direction and distance A from centroid in z direction. And what you can do is you can convert this eccentric loading into the our reaction N and M. Okay, so our reactions N and V and M and T, all of them are defined on and with respect to centroid position. Okay, so to convert this to equivalent problem composed of N and M, yeah, this is what you have to do. Yeah, so you have to consider N working on at centroid point, okay, and the size of N must be same as P so that you have exactly same force in X direction. However, even though you place N at the centroid, even though you say that okay, forces are equal to each other, you cannot say and you cannot somehow make up the moment contribution from P. Okay, so because P is not located at the centroid, due to this P, you're gonna have some moment in Z direction and moment in Y direction. Okay, so how can you obtain the mg directional moment? So regarding the mg directional moment, what you can see here is you have regarding this g-axis you have distance b and you have force p, so you have to p times b as the magnitude of mg component, and regarding the y-directional moment, you have to multiply a and p so that my equals to be p times a. Of course, when p is not located here, when p is located here, you gotta be careful about determining the sign of my and mg. Okay, so by making these conversion, like by considering n and my and mg, you can make a equivalent problem with original problem. Okay, so you have equivalent force, equivalent moment in z, equivalent moment in y. Okay, after making this equivalent problem, we already know the answers for each. Okay, so we can decompose this problem into n problem and my problem and mg problem, and you can write down the stress distribution sigma x as a function of y and z position like this. This is from n, this is from mg, this is from my. Okay, and you can of course find neutral plane from this equation. 0 equals to be all those equations. Okay, so you can see that we are adding one more complexity. So at least in previous example, even though our moment was not parallel to neutral plane, you can see that at least this neutral plane went through the centroid point, right? However, when you have these kind of thing, in addition to y equals to be some constant g, which is tangent phi g, you're gonna have some additional constant. Okay, the implication here is that if this is a centroid point, your neutral plane will not go through the centroid point. Okay, so what you can see here is like we are like gradually adding complexity and complexity, and that's how this textbook is written. Of course, before the midterm, I'm gonna make you like I would say like an entire summary of the contents in midterm. Then you're gonna have like an even bigger picture on how the loading and stress distribution becomes like a gradually complex as we are going through like more and more advanced concepts and chapters. Okay, so yeah, anyway, let me give you additional comment in summary lectures. And regarding the general eccentric loading, yeah, this is it. Like I don't have anything more to say. Okay, so and you can try to solve some example problem on this. And regarding the stress concentration, yeah, same. Okay, so here the two example geometry we're gonna consider is following. Yeah, this is our quite familiar geometry. We have large diameter d here, not diameter, large height d and small height d, and we have this radius curvature at the joint. Okay, when you apply the moment couple m here, depending on the ratio between large d and small g, and depending on the ratio between small r and small d, yeah, you can determine stress concentration factor k, and based on that, yeah, you gotta be careful about designing the structure on the bending. Yeah, of course, you have to obtain your maximum stress at this section. Okay, and after obtaining maximum stress at this section without considering stress concentration factor, then you multiply k. And it's the same for here. Instead of having the change of the height, you can have some sort of like a small notches here. Okay, so when you have this small notch, of course you can expect stress concentration. Okay, so actually, yeah, when you try to break some like a bar, I think most of you already know how to easily break the bar, right? You try to make a little dent or crack, and if you try to bend this bar after making crack, you can see that it'll quite easily break here. Okay, so it's not just the matter of having smaller cross section. Yeah, it's also about magnifying the stress due to stress concentration factor. Okay, and of course this stress concentration factor is function of the ratio between large d and small d. Small d is the width at this thinner point, and it also depends on the ratio between small r and d. Small r is the radius curvature of this little crack and dent. Okay, so based on these two ratio, you can determine k, and you can use this k factor for designing mechanically reliable structure. Okay, so regarding real example problem, I'm gonna discuss this structure in the last page of today's lecture.